Welcome back to another Jogamin video. This is part 2 of deriving moment of inertia equations for some shapes. This is the second shape. We have a total of 3 shapes. It's part 2 out of 3. Unfortunately, Matt Cube cannot make it anytime soon. I think that Pal got like deleted or something. Anyways, this shape, like I promised 2,000 years ago, or last video, watch it, is a square, or yeah, a rectangle in the middle, rotating from the center mass, or geometric it, where it's a uniform object, or so, anyways, watch, mass circle. Okay. Takes the middle. So, please bring this way, and it's rotating this way around its center. So, yeah, I'm call this on this x, call this x on the B plane. What is x is on this x? We're calling over this y. Actually, yeah. Oh wait, hold on. Okay, this is height is x. This is and this height is y. This is y. And this axis right here, the thickness is right now lighting time on y. Let's try to integrate. Start I equals r squared dm. And this is since we are rotating from the center shape right here, and we're gonna get the mass distribution from all the way here. So let's show that the dm will be this shape right here. Yeah. Let's assume that it's a really good drawing, but I don't know. Yeah, and it's pushing this way. Actually, just put the axis. Wait, let me extend it here. Yeah, extend it here. I mean, since it's a uniform shape, you don't need to how should I call this? It doesn't matter where you draw your shape as long as it's consistent with your entire method. But let's just assume this is what we're calling. Calling this whole length as c, this whole length as y over 2, because y is this bottom part of the shape. The bottom part of the shape. Let me draw it to be. This is what it looks like. Half of it is on the bottom side, so we're basically getting y over 2, and for the z side, we're getting the whole side of it, so we're getting the whole length of it. Alright, so remember, we're moving this way, so that's dr, and that the density of this shape specifically is sy, z, or I should say the whole shape of this section right here. When dr is at x. Actually, I don't even wait. No. Hold on. This x, the 4x is x over 2. It's x over 2 actually. So x over 2, y over 2 times z over mass. I tested it, works. It's just that I don't know why you chose y over 2 if I'm making it simple. I just want to get started from the edge at negative x. Wait, no. This is 0 and this is x. Holy crap. Yeah, I don't know if I wrote this right now or later, but yeah. X over 2 because we start. This is x over 2. Yeah. I don't know why. I could have just started at negative x over 2 with the bounds and then to x over 2. Anyways, so rho equals 4m xyz. And like I showed before, so dr is going to be changing, and y over 2 and z are constants, so y over 2 times g times dr integral r squared, and guess what? These, so then that's 2m over x. Wow. X integral r squared dr comes down 0, times 0 and x. Okay, so that's r cubed, and then x cubed over 8, and then times 1/3 times 2x, that's just equal to x squared over 12m. There you go. Yeah. Still got 8 minutes, right? I'll show you the easier way, because of all the simplification, you might as well just do it in 2D. Okay. So, it's in the middle, and this is defined, this length is x, y, so this is x over 2, y over 2. And this time, I want to show you that you can do it this way. You can define dm as this, or you can define dm as this, or you can define it over here. It'll still give you the same answer. Since we have a bunch of time, I can probably show you that they're equal. Anyway, so since this is always y over 2, linear density rho sigma equals y over 2 times x over 2. For this thing right here, this is all small part. The full density is x over 2 over m, so that's just 4y x m. Wow, doesn't that look familiar? Anyways, dr, yeah, dr equals dr times y over 2. Wow, this is getting way too familiar, guys. M over x to integral dr r squared, and that's literally what we got previously, so I'm not going to show you that. Oh yeah, no, instead of x over 2. Now, I'm not going to do the math for this one. In fact, I'll just tell you. This function, if this was a function, and say this portion, this other half did not exist, if this was a real function, and we're integrating from here to here, and since this function is symmetrical, and it's an even function, meaning, if I put even function means, if I put equals f of negative x, alright? So this here corresponds to exactly here, but this is just on the negative side. And so since these 2 points are on opposite sides with opposite signs, we can literally just write this as scroll down right there. So remember it was r cubed, so then x cubed over 8 minus x cubed over 8, right? So that's 2 times, so that's x cubed over 4 times 1/3 exponential. And then you're, yeah, so because because the distance now is just x, right? So that means the density will just be m over y over 2x times y over 2 dr. These cancel, so that's why double the distance, and then was double the distance, but then that little f of x over 2 minus f of x negative x over 2 just equals to I don't even know. It cancelled out. If you're watching this and getting confused about my talk of twos, just don't worry about it. Just know it's the same. It's all the same. So probably like the last 3 minutes of me talking was probably like wrong, other than the fact that this is equal to the same thing now. Since it's symmetrical this way, and this way, you can do it whatever you want. Next video, please.